So the standard change in free energy determines the spontaneity of a reaction. K, the equilibrium constant, determines how far the reaction goes towards the products. Larger K is going to go more towards the products. Smaller K, it's going to favor the reactants. If we have a larger K, we'll have a more negative delta G. The products are favored. Smaller K, we have a more positive delta G. The reactants are favored. So I gave myself there the task of deriving the relationship between K and delta G. So we'll start out with that equation that we've been using. So delta G for the reaction is equal to the standard delta G plus RT natural log of Q. So at equilibrium, what do we know about Q? It's equal to K, right? So at equilibrium, we could cross off Q and write K in there. What is delta G at equilibrium? It's 0, right? It's not going to go forward or reverse. Nothing's going to happen. So delta G is equal to 0. So now we have 0 equals standard delta G plus RT natural log of K. So we can move delta G to the other side. That's going to be RT natural log of K. And we don't really like that negative sign on the left side, so I'll multiply everything by -1. So multiply everything by -1, and there's the minus sign. And that makes a plus. So the standard change in free energy is related to the equilibrium constant. Any questions? No? So here we've got some more pictures. So here we have an equilibrium between two gases, and K is less than 1. So K less than 1 says that the extent of this reaction will be small. It'll be mostly products rather than favoring the reactants. So if we start in the middle with an equal amount of each component, that would be standard conditions, because you'd have a partial pressure of 1 atmosphere for both of them, right? We start here with PA and PB is equal to 1 atmosphere. Then Q is going to equal 1. And we're going to end up with positive delta G. The reverse reaction is spontaneous. Over here, if we've got K being larger than 1, then in this middle place where we have equal amounts of the product and the reactant, Q is equal to 1, but it's going to go forward. So what am I doing there? I'm using that that equation we just derived. So if K is a big number, let's say 10, right? So negative RT natural log of 10. The natural log of 10 is 2.3. R and T are always positive numbers. So we've got negative RT times 2.303. And we can say that delta G is negative. Do you see how I did that? I just plugged in some random number. This is saying if K is bigger than 1. So I'm like, well, let's make it 10. The natural log of that is a positive number. When I multiply it by R and T, also positive numbers, it's still positive, and then we've got this negative sign. So delta G has to be less than 0. Over here, where K is less than 1, we could do a similar thing. Delta G, standard delta G, is equal to negative RT, natural log of, let's say it's 0.01. The natural log of 0.01 is negative 4.6. So this is going to be a positive number, right? If K is equal to 1, then standard conditions, Q would be 1 and nothing would happen. It would just remain at equilibrium. Any questions? Does that make any sense? Good. So if we know K, we can calculate the standard free energy change. So here we've got iodine and chlorine reacting to form iodine chloride, and Kp is 81.9. Is delta G going to be positive or negative? Negative. But we can calculate it, and that's what we need to do here. So delta G is equal to negative RT, natural log of K. We've seen that for most of these delta G's, we've used units of kilojoules because that gives us a better sized answer. So I'm just going to be preemptive and express R in kilojoules. It'll probably backfire on me because I did the opposite in the first one. Oh, forgot the negative sign. That's going to be a problem. Minus temperatures 298 K. Kelvins cancel out. And then we've got the natural log of 81.9. So my standard enthalpy change here is negative 10.9 kilojoules per mole. Negative. Any questions? So the free energy change depends on the equilibrium constant. The free energy change also depends on the temperature. Because with that earlier reaction, standard free energy change is equal to the standard enthalpy change minus T times the standard entropy change. Yeah, I'm supposed to derive something here. So this is delta G0, this is delta G0. How about we just set those two things equal to each other? Seems like a good idea. So negative RT natural log of K is equal to delta H minus T delta S. So I could divide both sides by negative RT. So over here, I'm going to end up with natural log of K. This mess can be expressed as negative delta H over RT. These two negatives are going to cancel out, plus T delta S over RT, and the T's cancel out. And so we can straighten this up a little bit. Natural log of K is negative standard delta H over R times 1 over T plus delta S over R. That look at all familiar? We did an experiment where we graphed that, right? We graphed T and natural log of K, and we were able to calculate delta H and delta S. So that is this equation right here. This is the straight line form of that. So natural log of K would be graphed on the y-axis, 1 over T on the x-axis, and we should get a straight line. The slope is equal to negative delta H over R, and the intercept is delta S over R. So you put it in Excel, you get a straight line equation, whatever the slope is, you plug that in here, you know what R is, you can calculate delta H. You stick the intercept in here, you can calculate delta S. Now this is useful over a limited temperature range, but it's still useful. And so we can find delta H and delta S by measuring K as a function of temperature. That's what we did in experiment 18A. We can also express that as a 2-point form of the line, and we can get delta H by measuring the equilibrium constant at 2 different temperatures instead of doing a whole bunch of them. So if we know what, the other thing we can do is we can find an equilibrium constant at another temperature if we know what delta H is and we know the equilibrium constant at one temperature. So we can use that to find the equilibrium constant at another temperature that we might be interested in.